balancing two half reactions using the electrons to balance it, finding out what the half reaction cell potentials are, looking them up, and adding them together. This is just there because remember we have to flip one of them, but we're still going to add them together. If E is positive, then it's thermodynamically favored. If E is not positive, it is not thermodynamically favored. So let's practice this again. This time I'm not going to give you the two half reactions. We're just going to go back to what we did before. I'm going to give you the complete balance electrochemical reaction, and then you're going to calculate the cell potential, and then whether, using the sign, determine whether it's favored or not. So as this is written, let's write down, let's pull out the two half reactions. So I've got 3 silver going to 3 silver plus 3 electrons. And then my other one, I have aluminum 3 plus, right? Plus 3 electrons goes to aluminum solid. Okay, I looked these up in the textbook for their cell potentials next. All right, now if I write this in terms, let's go to the table because, so let me go here and here. Okay, now if I want to look at this in terms of their, remember everything is going to be written in terms of reduction potentials. So if I come over here, I've got silver plus 1 electron is 0.8. So if I go back to my problem, what I've done here is I've flipped it. So what I'm going to use as my cell potential is a minus 0.80 volts. So let's go back and look at this again so you know what I did. I came over here. I found my reduction potential for silver, which is right here. That's 0.8, but I'm going to flip it because in my reaction, silver is on the left. So I'm going to flip that, and so my potential is going to be minus 0.8. All right, let's go back to the table again. And this time I've got aluminum, and it's aluminum 3 plus here. In this case, I'm going to leave it because my aluminum is being reduced. That's a minus 1.66. So this one is a minus 1.66. So that means that my potential is a negative 2.46. That means it is not favored. Okay. All right, let's look at the second one. We're going to pull our two half reactions out. I've got SN2 plus goes to SN4 plus, and this is going to have to be here 2 electrons because I've got to have 2 and 2, so that's 2 plus and 2 plus. Then I pull out my iron. I've got 2 Fe3 plus goes to 2 Fe2 plus, so that is going to be 2 electrons there. And so all this balances, and those are my two half reactions. All right, so let's look at what I've got. I've got a different table this time. I had to find one that had in there. Okay, so let's find the tin 2 plus. That's this one here. Now notice that this is the reduction. It's 0.15. There it is. But what I have is I have the oxidation. So this is going to be a negative 0.15 because I'm going to flip it. The iron reaction is right here. I'm going to take iron. Sorry, I'm looking at the wrong one. It is right here. I'm going to take iron, I'm going to add an electron. I'm going to make iron 2 plus, and that's 0.77. Of course, I've multiplied by 2, but it doesn't matter because the 0.77 stays. So this is a 0.77. And so I get for this one a positive 0.62 for that one. So that's a 0.62, and that is favored because that's positive. So I want you to go through. I'm going to give you the rest of the answers to these. I promise you 100% you will have a problem exactly like this one, where you will pull it out, you will find out what your cell potentials are. So I would recommend, here are 2 problems to work and their answers. And you can do that and see if you can come up with the right answer for that one. Okay, so now here's where I'm going to start to slow down a little bit. So I'm going to cover the same amount of material, but there's some concepts here that you need to know about electrical currents and things like that I've got to go over to help you with these problems. All right, so the next thing we're going to do, we're going to go to our formula chart, and we are going to start looking at these 3 equations. So we need to get from here. We got to do here, then here, then here, then here. And I've kind of highlighted this, and I'm going to talk to you about why I've done that, but we'll do that in a minute. Okay, so one of the things that we can do is we can relate now our E of our cell to delta G. And so in the equation, N is the number of moles of electrons. So if I go back to this, N for this reaction would be 3, and N for this reaction would be 2. It's the number of electrons that you use to balance the 2 half reactions. So now that we've got this, what we're going to do is we're going to do a large problem where we're going to calculate E, then delta G, and then we're going to be able to calculate K. All right. So we're going to start off with, here is our equation. Now, what we want to do first, I'm going to put a 1 here, a 2 here, and a 3 here. So I'm going to start off with number 1. If I want to calculate E, then I'm going to use my 2 half reactions, Zn2 plus 2E goes to Zn, and the E for this value is actually a negative 0.763 volts. If I look at my half reaction for copper, I get copper, and this one is 0.337 volts. Remember, so I'm doing a little bit the long way. When I do this, if I want this to be positive, I'm going to flip this one, which is exactly what you see here. So I'm going to have Zn goes to Zn2 plus 2 electrons, and that's going to be 0.763. Cross that out, and I get Cu2 plus zinc goes to copper plus zinc 2 plus. I add these all together and I get 1.1 volts. I think this should be familiar to you because that is the one that we looked at in our simulation. All right, now if I want to calculate delta G, right, I can take delta G, we're going to use the equation up here, and we're going to say that delta G is equal to N times F times E. Now before I do this, one of the things that I wanted to show you is kind of talk about the units here. Now N is the number of electrons that you're transferring. I'm going to rewrite this here so that I can do this underneath. Right? Let's look at F. What is F? If you go to your formula chart, F is here, and it's right here. It's 96,485 coulombs per mole of electrons that you used to balance your equation. So what I'm going to do is I'm going to put, this is moles, this is coulombs per mole, okay? And then if you look at E, E is volts, but volts is equal to joules per coulomb. You don't have to memorize all this, I just want you to see it. This is equal to joules per coulomb. So what happens is I end up crossing this out, crossing that out, crossing that out, and crossing that out, and I end up getting delta G in terms of joules. Now notice that what does that mean? We are going to want to express delta G in terms of kilojoules. So you can either convert this to kilo, or when you get to the very end, you can convert this. So we're going to stop here. I'm going to go to the next video and we'll continue the problem.